Okay, thank you. First, let me thank the organizers for the opportunity to talk about quantum groups again with somebody. Since last half a year, I spent taking care of my son, and although he already can count up to 10, I wasn't able to teach him quantum groups yet. And yes, so in my talk, I would like to focus on quantum symmetries. And at the beginning, I should say, I'm interested in a bit different quantum groups that most of you probably are. I'm interested more in those free quantum groups, not that much in those deformed ones. So this is why I decided to give a bit more general talk. And I will most probably say about my own research just a couple of sentences. And this couple of sentences are theorems that I wrote here. So this is my last result, saying that every Hadamard matrix or Hadamard graph of size at least 4 has quantum symmetries. And secondly, that all Hadamard matrices of a given fixed size are usually quantum isomorphic. So the goal of my talk will be to try to fill those blackboards and directly here. And during that, I hope that I will roughly explain you what those theorems mean. And most importantly, I believe that the most interesting thing should be the tools that I use for that. And those are diagrammatic categories. Good, so we can start. What are symmetries or quantum symmetries? So usually studying symmetries, you have some space, let's say space X. And classically, you study symmetries. And studying symmetries, you typically obtain a group, right? And as you can guess, if you study quantum symmetries, you should obtain a quantum group. I guess you can guess how this somewhat works. So having a quantum group, this quantum group can act on a space or a co-act on some algebra, something like that. And we are typically interested in the largest possible quantum group that acts or co-acts somehow faithfully on some space. And that's we can call the quantum automorphism group of that space or something like that. But in my talk, I would like to focus on a bit different viewpoint, namely that I would like to study the quantum symmetries not in terms of quantum groups, but in terms of categories. So I will obtain some category. I will explain how do I obtain it. But those two approaches are indeed equivalent because there is what some of you may know, this so-called Tanaka-Schrein duality. Yeah, which says those two are equivalent. Again, I don't have time to explain this in more detail, but in case you're familiar with that, well, if you have a quantum group, you can construct in its representation category, and that's exactly this category. On the other hand, if you have some category with some special structure, you can always reconstruct the corresponding quantum group. Right. So now, and these categories, I will often realize or describe by diagrams. So now how those diagrams work. Well, I will typically have some underlying vector space. So let's say Cn, something like that. And I will be interested in describing what physicists call tensors. So some linear maps from between tensor powers of this vector space. And so for instance, I can have a linear map A from V tensor V to V, or I can have some other linear map from V to V tensor V and so on. And how do I describe these linear maps? Well, this A, this is something that takes two vectors and gives you one vector. So you can view this as a black box A that has two inputs. You put the two vectors there, and it is one output. And similarly, this B, this is the same thing, except it has just one input and two outputs. And now what you can do, well, you can somehow compose those two together. So remember, I'm from the Faculty of Electrical Engineering, so I'm basically doing those electrical circuit diagrams. So like A composed with B, what does that mean? Well, I take my input and I put it into this B, and now I have the two outputs in those two wires here, and I put those outputs as an input into my A, and then I have, again, a single output, and that's it. So the same thing, the same way you can compose it the other way around. So first you apply A on your two vectors, and then use the result as an input for B, and that's what is B composed with A. And you can also do other things. For instance, so you can take this A with two inputs and one output, and your B with one input and two outputs, and put them side by side. And again, you have a diagram or circuit, or how do you want to call it, with three inputs and three outputs. So what this diagram describes? Well, for the first two outputs, you apply the A. For the third one, you apply the B. So this is exactly the tensor product, right? Basically, if you want, you can also, if you need, which I do, you can also do some involution. So if you do conjugate transpose of this A, you obtain, again, some box which goes the other way around. So I will denote that by a dagger that would have one input and two outputs. But you can do all sorts of things, like you can take this A and as an input, use another A, and maybe somewhere you also have B here, which is two outputs, and you use those two outputs and put them to a dagger, and you build all those stuff. And what I will often talk about is what I will call a category generated by A and B. So this will be denoted like this. And what I mean by that is the set of all linear maps that can be made out of A and B using these operations: composition, tensor product, and involution. So by the way, if I say a category in my talk, I will always mean monoidal dagger category. So I always have the linear structure, and I always do not only have the composition, but also the tensor product and the involution. And so by construction, all those pictures that I draw here, all of them are elements of this category. And on the other way around, this category precisely contains exactly all linear maps that can be described by those pictures, and maybe linear combinations of those. Right, so this is the categories I will use. And now let's get back to the symmetries. So what is a symmetry? So I said you have some space you want to study the symmetries of, and the space typically has some structure, and the point of symmetries is that you want to preserve this structure. So how that works? Well, I think the most typical example is that if you have some vector space V, I don't know, maybe complex or real. Let's not go into the details here. And you often have, this is often equipped with some bilinear form. So bilinear form is a linear map from V tensor V. to C. And you often want to preserve this bilinear form. Let's say this is the standard one, just given by the Kronecker delta. Well, what classically you would do, you would, constructing this group, you would just consider our linear maps that somewhat preserve this beta. So beta composed with T in the appropriate tensor power. So here, T tensor T equals, again, T in the tensor power, which is now 0, so equals beta. And what is this? This is just the orthogonal group, right? So this is your group of automorphisms. You can do the same for quantum groups, and you obtain the free orthogonal quantum group ON plus. I won't give the details here. As I said, I want to focus for the category. So what category do you associate to this beta? Well, remember that I said that you need to preserve this beta. But if you need to preserve this beta, you also need to preserve, well, for instance, beta tensor beta, because that only depends on beta, right? You also need to preserve beta Degger. You always need to preserve anything like beta composed with that beta tensor beta composed with identity tensor beta Degger tensor identity, or anything like that. So basically, you need to preserve the whole category generated by this beta. So solely from this viewpoint, it's worth studying this category. And actually, writing this down into this picture, this category is exactly what corresponds by this Tanaka trend duality to the free orthogonal quantum group. And so now we want to study this category. So how do we do that? From the first sight, it's not at all clear how this category look like, how many elements it has, like what are the dimensions of the morphism space, or those things are not at all clear, because there's infinite, if you like fix the tensor powers here, like here, there's infinitely many possibilities how to build such a tensor from this beta, right? So the tool we use are diagrams. Okay, so how is that helpful? Because there's infinitely many diagrams involving this beta that have, I don't know, k inputs and outputs. Well, the first important thing is to use convenient notation. So this beta, which has 2 inputs and no output, this is actually usually denoted by such a cap. And the beta Degger with 2 outputs and no input is usually denoted by this cup. And now, a second important thing is that if you do such a composition, so you first take some vector and tensor it with this cup. And then to those first 2 things, you apply the bilinear form, so the cap. And here, again, nothing. Here's just identity. Then this is the original vector. So this map is just the identity. And the other way around, it works as well. And therefore, what is the consequence is that you can have any sort of complicated picture here, like involving all those cups and caps, like, I don't know, like that, or maybe like that. I don't know what else. Like this. And it has five inputs and 1 output. But what that equals to, thanks to this relation, you just take the 5 inputs and 1 output, and you just follow the lines. This is connected to this. This is connected to this. This is connected to this. And what I forgot to say, if you compose beta and beta dagger, you obtain the dimension of your vector space. So for this loop here, I have the n here, and that's it. And therefore, this category generated by beta, this is by diagrams described by all pairings. So if I take the morphism space with k inputs and l outputs, then those will be pairing of k plus l points. And actually not all pairings, but just the non-crossing pairings, because using these operations, I'm never able to construct a crossing in my picture. And that's it. And yes, we already have heard on Wednesday, if you fix k plus l, the number of pairings is given by Catalan numbers. So now you know a lot more about this category, and most importantly, you have finitely many diagrams for each morphism space, so you can explicitly write down what are the elements. And actually, it turns out that if this dimension n is at least 2, then this description is actually faithful. So there's bijection between. So this is really a basis of those linear maps. Okay. Now let me say something a bit more concrete, because now I didn't really say what my underlying space here is. Symmetries of what am I studying? So the most simple example for me will be the finite set. So yeah, I should say I will focus, or I focus on just finite spaces equipped possibly with some combinatorial structure, because it turns out that these have the remarkable property that even if you start with a classical space, just a set of points, this actually has quantum symmetry. So you obtain really a quantum group, not a group. This usually does not happen if you have some continuous thing. So finite set. So what is a finite set? Finite set is just a finite set. So just a set of some points. Well, this is not a vector space. I am used to work with vector spaces. So how do I make a vector space out of it? Well, as usually in non-commutative geometry, instead of that, I study the algebra of functions over that space, which is n-dimensional, spanned by the canonical projections. And this will be my vector space here. But I don't only have a vector space, I have an algebra. So this is equipped with the multiplication, which works like this. Those are, as I said, projections, which is not so important. The important thing is that I have some structure map here. I have a multiplication that goes from B tensor V to V. And this is what I need to preserve. And by the way, those cops and caps, they are somewhat important in those categories. So I always also need some inner product or bilinear form as well. So I will define the obvious bilinear form here, which is the second thing I also want to preserve. And that's it. So now let's make diagrams out of it. So this is M, 2 inputs, 1 output. This is beta, 2 inputs, no output. And now let's find some convenient notation. So this is often called spiders. So I will have such a dot with k inputs and l outputs. This will stand for a linear map. So let me describe this linear map using the matrix entry. So it has k inputs and outputs. So it will have k plus l indices. And this will be defined just by Kronecker delta. All the indices have to be the same. Well, that sounds convenient because then this n is just equals to this, and this beta this just equals to this. And moreover, if I have any, again, now I should say what are the reduced diagrams. So if I have any complicated diagrams with a lot of dots that are somehow connected together, maybe like this, and like that, and I don't know, like that. Again, the only important thing is which lines are connected to which, thanks to this Kronecker delta. Those, getting back to those electrical circuits, those are really just like the nodes in the electrical circuit, where all the wires are connected together, and that's it. So this actually equals to, and now you only look how those points are partitioned together. So the result is just a partition of the inputs and outputs. So those three are connected together. Those three are connected together. Those two are connected together, and all the others are connected as well. The result looks like this. Again, the category I'm interested in, generated by this n and beta, is described by non-crossing partitions. And this is what we also have heard already on Wednesday. Good, so this is how it works somehow. And now, what are the applications of that? Well, or maybe just to stress how it works in general, you have here this space. This is some vector space equipped by some structure maps, and the associated category is usually just the category generated by the structure map, because the structure maps is what you want to preserve. And now, what is this good for? Well, first of all, you can tell whether space has quantum symmetries or not. So as I said, associated to this category, there is really a quantum group, and you are interested whether the quantum group is a group or not. And how you tell whether quantum group is a group? Well, you have to look whether it is commutative, and you can tell this looking at the category, namely, you just look whether the category contains the flip map sort of as a braiding. So effect X, space X has no quantum symmetries. So the quantum group is a group if and only if, and now this is slightly confusing, this is not an X, this is a diagram which stands for the flip map, because I flipped the two vector spaces. If and only if the flip map is inside the category. Oh, I'll just write C. Right. So this is what makes it interesting. So if this flip map is not in the category, then there must actually exist some quantum group here. There must exist some matrix with non-commutative entries that provides this symmetry. And this is what we sort of have proven here, although this is a bit cheating because, well, obviously the crossing is not in the diagrammatic category here because I constructed it that way. It still may happen that, well, some linear combinations of this diagram actually equals to this crossing, but actually it turns out that it does not. So we really have a quantum group, which is called the free symmetric quantum group, which was defined in '98 by Wang. And now this is a diagrammatic sort of a proof that it is a quantum group. And so there's a first application explaining a bit the first theorem here. And the second application, well, suppose we didn't want to study finite sets, but quantum sets, quantum spaces. How a quantum space, finite quantum spaces. What is a finite quantum space? Well, just an ordinary finite space that's essentially commutative, finite dimensional commutative algebra, maybe equipped with some bilinear form. Then what is a quantum space? That's a non-commutative algebra, right? And again, we need the bilinear form, and we actually need some certain condition, which is called being special. So finite quantum spaces are so-called special Frobenius star algebras. And this special condition, what it does is that it allows you to copy paste this thing. So again, you have a multiplication and a bilinear form, and you build those partitions. So the associated category is again the category of all partitions. So the category as an abstract category is the same. Does that mean that the quantum group is the same? Well, it doesn't, because in this Tanaka-Klein duality, there is a one-to-one correspondence, but the category there, it is the concrete category concretely realized by some linear maps. If you have a category which is isomorphic, but different, you can obtain a different quantum group, which is so-called monoidally equivalent. So those quantum groups are different, but we call them, or we call the space being quantum isomorphic. So I will just write it. X1 is quantum isomorphic with X2 if and only if the first category is isomorphic to the second one. And this really has, again, quantum group meaning. Again, if two spaces are quantum isomorphic, this means that something has to hold here, namely that there must exist sort of like a matrix with non-commutative entries that intertwines those two spaces. Somehow, somebody mentioned the notion by Galois extension. That's exactly what happens here. Let's not get to the details, but what you can see, the result we obtained here. So out of the first fact, we had that finite spaces have quantum symmetries, and out of the second fact, we obtained all those categories are the same, and therefore all finite quantum spaces of a given size, because you can spot the size by this relation, are quantum isomorphic. Right. And now you can put additional structure into this space here, for instance, putting there an adjacency matrix. You can study quantum automorphism of graphs. You can put several adjacency matrices and, for instance, study quantum isomorphisms or automorphisms of association schemes or whatever. By the way, for the graphs, this means that the adjacency matrix will appear in the calculus, but for graphs, you're not able to make some general reduction rules that would work for every graph, because this would mean that all graphs are quantum isomorphic, but that's not the case, because, well, the adjacency matrix can be arbitrary, and you don't have like relations that would hold for every matrix, right? So this is a bit inconvenient. But what I was able to do is to build this theory for Hadamard matrices. And I obtained exactly those two results, that they have symmetries, quantum symmetries, and they are all mutually quantum isomorphic. So that's it. Quantum isomorphic means that the associated categories are isomorphic or monoidally equivalent. Although, well, here I didn't tell you what the category is. It's a bit more complicated than just putting the Hadamard matrix there. But
by quantum matrix, using the symmetry of the graph.
Yeah. So this is connected to that. So yeah. So quantum symmetries of graphs, how that works is that you simultaneously permute rows and columns, right? And that is exactly described, you can exactly describe that by just putting the adjacency matrix into that category. And this is what describes you the quantum automorphism of an adjacency matrix. Now, for Hadamard matrices, the classical notion of so-called equivalence of Hadamard matrices is a bit more complicated. They are called equivalent if you can obtain one from the other by permuting rows and columns separately, and also by multiplying them by ±1. So those are the moves you can do. So this is a bit weaker definition. So what I did is that I quantized this definition, which then requires a bit more work than just putting the matrix in the category, and that's it. If I did that, they would not be quantum isomorphic. Yeah, but for this notion, I did it. And regarding the graphs, well, classically, since this notion is somewhat complicated, what captures the classical symmetries of Hadamard matrices is so-called Hadamard graphs. So this is not just taking the Hadamard matrix and considering it as an adjacency matrix, but it is somewhat more complicated, constructed exactly the way that automorphisms of the matrices correspond to automorphisms of the graphs. And the same works for the quantum ones. Yes, so well, there's the notion of bi-Galois extensions that somehow, well, quantum groups somehow describe the automorphisms, right? And if you want to describe quantum isomorphism, then it is something like quantum group, again, let's say matrix with non-commutative entries, but now it does not act on one space, but it sends one space to another. So if you want to formalize this, then this is called the bi-Galois extensions. And this is equivalent to the fact that the associated categories are monoidally equivalent.
Thank you very much.